Hi, this is Brandon Rohr with How Decision Trees Work. Decision trees are one of my favorite models. They're simple and they're powerful. In fact, most high-performing Kaggle entries are a combination of XGBoost, which is a variant of decision tree, and some very clever feature engineering. The concept behind decision trees is refreshingly straightforward. Imagine creating a data set by recording the time you left your house and noting whether you arrived at work on time. Looking at it, you can see that for the most part, departure times before 8:15 result in punctuality, and departure times after 8:15 result in tardiness. You can summarize this pattern in a decision tree. The very first branching point is the question, did departure occur before 8:15? There are two branches, a yes and a no. For consistency, we'll keep all of our yeses on the left. Placing this decision boundary divides the data up into two groups. And although there are some stragglers and exceptions, the overall pattern is captured by placing this decision boundary at 8:15. If you depart before 8:15, you can be reasonably sure of getting to work on time. And if you depart after 8:15, you can be reasonably sure of being late. This is the simplest decision tree possible, a single branch. We can refine our estimate of punctuality by subdividing both the before 8:15 and the after 8:15 branches. If we add additional decision boundaries at 8 o'clock and 8:30, then we can divide up our arrival estimate more fully. Those before 8 o'clock are confidently on time. Those between 8 and 8:15 are probably on time, but not guaranteed to be so. Similarly, departure times after 8:15 can be divided into those after 8:30, which are almost certainly late, and those before 8:30, which still have a small chance of being on time. This decision tree has two levels. Decision trees can have as many levels as you want. Most often, each decision point or node has only two branches. This example has a single predictor variable and a categorical target variable. The predictor variable is our departure time, and our target variable is our punctuality, whether or not we're late. Because it has only two distinct values, it's categorical. Decision trees with categorical targets are also called classification trees. We can extend this example to the case where there are two predictor variables. Consider both the departure time and the day of the week. We'll start counting at Monday equals 1, so Saturday equals 6, and Sunday equals 7. Inspecting the data, we can see that on Saturday and Sunday, the green filled donuts, representing being late, extend further to the left. This means that leaving at 8:10 is probably sufficient to get you to work on time on a weekday, but probably not on the weekend. To represent this in a decision tree, we can start as we did before by putting a decision boundary at 8:15. Any departure times after 8:15 are likely to be late. Departure times before 8:15 are inconsistent. Before, we assumed that they would be on time, but now we can see in the data that that's not entirely true. To make our estimate better for the weekends, we can subdivide the before 8:15 departure times into weekday and weekend. Now, a weekday departure before 8:15 is confidently on time. However, weekend departures before 8:15 are mostly on time, but not entirely. We have updated the decision tree with a node that reflects this new decision boundary. Now we can further refine our estimate by subdividing our weekend pre-8:15 departure times into before and after 8 o'clock. Before 8 o'clock, almost all of the arrivals are on time, and between 8 and 8:15, the majority of them are late. Now we have our two-dimensional decision tree neatly divided into four regions. 2 of them reflect on-time arrivals, and 2 of them show late arrivals. This is a 3-level decision tree now. Note that not all the branches need to extend down to the same number of levels. Now we can look at an example with a continuous target variable rather than a categorical one. When a model is used to make predictions about continuous numerical variables, it's also called a regression tree. So far we have looked at 1- and 2-dimensional classification trees. Now we'll look at regression trees. Let's consider the question of what time someone wakes up, as predicted by their age. The root of our regression tree is an estimate for the entire data set. In this case, if you had to make an estimate without knowing someone's age, a reasonable guess would be 625. This is the root of the decision tree. A reasonable first split is at age 25. On average, people younger than 25 wake up at 7:05, and people older than 25 wake up at 6 o'clock. There's still a lot of variation in the younger group, so we can split it again. Now the people younger than 12 can be estimated to wake up at 7:45, and people between 12 and 25 can be estimated to wake up at 6:40. The over 25 group can be meaningfully subdivided too. Those between 25 and 40 wake up on average at 6:10, and those between 40 and 70 wake up on average at 5:50. There's still a lot of variation in the youngest group, so we can further subdivide it. By slicing again on age 8, we can refine the estimates to more closely fit the data. We can also subdivide the 40 to 70 group on the 58-year line. Notice that we're getting to where we only have 1 or 2 data points per leaf of our tree. This is a dangerous condition and can lead to overfitting, which we'll talk more about in a minute. The resulting tree lets us make a numerical estimate depending on someone's age. If I need to estimate the wake-up time for a 36-year-old, for instance, I can start at the top of the tree. Are they younger than 25? No. Go to the right. Are they younger than 40? Yes. Go to the left. The estimate then becomes 6:10 a.m. The structure of the decision tree lets you sort people of any age into their respective bin and make an estimate about their wake-up time. We can also extend this regression tree example to have 2 predictor variables. If we consider not only someone's age, but the month of the year as well, then we can find even richer patterns. In North America, days are longer in summer months, and it gets lighter earlier in the morning. In this completely unrealistic example, children and teens are unburdened by the rigorous schedules of work and school and have their wake-up time driven by when the sun comes up. On the other hand, adults fall into more regular patterns, fluctuating only slightly with the seasons. Again, older people in this example tend to wake up a little earlier. We construct this decision tree much the same as the last one. We start with the root, a single estimate that roughly fits the entire data set, 6:30. Then we look for a good place to put a decision boundary. We split the data on age 35, creating 2 halves, one for our under 35 population with a wake-up time of 7:06, and one for our over 35 population with a wake-up time of 6:12. We repeat the process, subdividing our younger population on whether it is before or after the middle of September, and whether it is before or after the middle of March. This isolates the winter months from the summer months. Winter months have a wake-up time of 7:30 for those under 35, and in the summer months it's 6:56. Then we can revisit our over 35 population and split them again on age 48 to get a more accurate representation. We can also go back and subdivide our under 35 winter wake-up times on age 18. Someone under 18 in the winter will wake up at 7:54 as opposed to 6:48 for those over 18. You can start to see the emergence of the tall corner peaks. As we make each additional cut, the shape of our decision tree becomes a little bit closer to that of the original data. Also, you'll notice in the upper right-hand plot that the decision boundaries begin to slice the dataset into regions of approximately uniform color. The next cut continues this trend, focusing on dividing those younger than 35 in summer months to those older and younger than 13. The shape of the model becomes even more similar to that of the data. You can imagine continuing this process until the model closely represents the smooth trend underlying the data. Each decision region would become progressively smaller. The approximation to the underlying function in the data would become progressively better. The power of decision trees is not without pitfalls. An important one to watch out for is overfitting. Returning to our example of a single variable regression tree, age versus wake-up time, imagine that we continued to make cuts on the age axis until there were only 1 or 2 data points in each bucket. When we get to this point, the decision tree explains and fits the data very well. It fits too well. Not only does it capture the underlying trend, the smooth curve that the data follows, but it also catches the noise, the unmodeled variation that's included in the measured data. If we were to take this model and use it to make predictions about new data, the noise from the training data would actually make our predictions less accurate. Ideally, we want a decision tree to capture the underlying trend, but not to capture the noise. One way to safeguard against this is to make sure that there are more than a handful of data points in each leaf of our decision tree. That way, any noise will be able to average itself out. Another thing to watch out for is having lots of variables. We started with a one-dimensional regression tree, then included month data to create a two-dimensional regression tree. Decision trees don't care how many dimensions we have. We could, for instance, also add latitude, the amount of exercise someone gets on a given day, their body mass index, and any other variables that we think might be relevant. To visualize this, we'll use a trick shared by Geoffrey Hinton, a renowned deep neural network researcher. He recommends, to deal with hyperplanes in a 14-dimensional space, visualize a 3D space and say 14 to yourself very loudly. The challenge when working with many variables then becomes deciding which variable to branch on when growing our decision tree. If there are very many variables, then this can require a lot of computation. Also, the more variables we add, the more data we need to reliably choose between them. It's easy to get into a position where the number of data points is comparable to the number of variables. When our data set is represented as a table, this manifests itself as the number of rows being comparable to the number of columns. There are methods for dealing with this, such as randomly selecting a variable to divide on at each branch, but it's something to keep an eye out for and handle mindfully. As long as you keep your eyes open for places where decision trees might fail, you're free to take advantage of their strengths. Decision trees are fantastic for when you want to make as few assumptions about your data as possible. They're quite general. They can find nonlinear relationships between your predictor variables and your target variable, as well as nonlinear interactions between predictor variables. Quadratic, exponential, cyclical, and any other relationships can all be revealed as long as you have enough data to support all the necessary cuts. Decision trees can also find non-smooth behaviors, sudden jumps, and peaks that other models like linear regression or artificial neural networks can hide sometimes. There's a good reason that decision trees consistently outperform other methods on data-rich problems. Thanks for tuning in, and I hope this is helpful in building your next project.
Bayesian inference is a way to make guesses about what your data mean based on sometimes very little data. The way it works is tricky, but it's not magic. It's definitely something that you can wrap your head around, and it's not impossible to do so. My goal is that by the time we're done talking, you'll have a pretty crisp picture of how it works. Bayesian inference is just guessing in the style of Thomas Bayes, who was a nonconformist Presbyterian minister. He wrote a couple of books, one about religion and one about probability. So Bayesian inference is just guessing in the style of Bayes. So to illustrate it, imagine that you're at the movies and someone drops a ticket. You pick it up and you can see them from behind. You know they have long hair, but you don't know whether they're a man or a woman, so you have to make a guess. Based on what you know about the attendees at your movie theater, you might say, "Excuse me, ma'am, is this your ticket?" Now imagine instead that this person is standing in line for the men's restroom. Knowing this extra piece of information, you might make a different guess. Bayesian inference is a way to capture this common sense knowledge about the situation and help you to make better guesses. So to put numbers to this dilemma at the movie theater, let's assume out of 100 women at the movies, 50 have short hair, 50 have long, and out of 100 men at the movies, 96 have short hair and 4 have long. In this case, we can see that there are definitely more women with long hair than men with long hair. So it's a safe bet to assume this person's a woman. Now we just made a subtle assumption that there are about the same number of men and women at the movies. This assumption no longer holds when we move to the men's restroom line. Here, let's say there are 2 women out of every 100 people and 98 men, maybe women keeping their partners company. There's still one with short hair and one with long hair. It's still half and half long and short hair, but now there are 4 times as many men with long hair than women with long hair in this group. Now the safe money is to bet that this person is a man. So to draw this a little differently, out of 100 people at the movies overall, we'll make this assumption explicit that 50 of them are women, 50 of them are men, so this is how the different categories break down. In the line for the men's restroom then, they break down a little differently. So to translate this to math, the probability that a person is a woman is the total number of women divided by the total number of people, 50%. Similarly for men. Moving to the men's restroom line, the probability that someone is a woman is 2%, 98% for men. Now, Bayes' theorem is a little bit tricky, so to be very precise, we're going to have to talk math. So if you bear with me for just 3 probability concepts, we'll lay the foundation for presenting Bayes' theorem. The first one is conditional probabilities. If I know that a person is a woman, that's the condition, what's the probability that that person has long hair? So it's written as probability of long hair given that a person's a woman. So to get this, we just divide the number of women with long hair by the total number of women, 50%. And this doesn't change whether there's 50 women in your group or 2 women in the group. Still, if we know that a person is a woman, the probability that they have long hair is 50%. We can do the same thing with men. Probability that someone has long hair given that they're a man is 4%. So conditional probabilities, if I know that B is the case, what's the probability that A is also the case? This is not, you can't reverse B and A and have this be true. So for instance, if I know that the thing I'm holding is a puppy, what's the probability that it's cute? The probability is very high. If I know that the thing I'm holding is cute, what's the probability that it's a puppy? Well, it might be a puppy, it might be a kitten, it might be a hedgehog, it might be a small human. There's lots of things that it could be. So the probability there is less moderate. So these things are not interchangeable in conditional probabilities. Now, concept 2, joint probabilities. So what's the probability that a person is both a woman and has short hair? So to calculate a joint probability, you first find their conditional probability. Well, if I know that they're a woman, what's the probability that they have short hair? And then you multiply that by the probability that they're a woman. So in this case, 0.5 times 0.5, we get a 0.25, which is exactly what we knew it was going to be. And the same is true for all of our different conditions. So we can do this for the men's restroom too. The probability that someone is a man and has long hair, 4%. Someone is a woman and has long hair, 1%. Joint probabilities are different than conditional probabilities. Here, the probability that A and B is the case is the same that the probability that B and A is the case. So the probability that I'm having a jelly donut with my milk is the same as the probability that I'm having a milk with my jelly donut. These two conditions, these two situations are identical, so we can swap the order. And finally, concept 3, marginal probabilities. If I wanted to say, figure out the probability that someone has long hair, I just add up all of the different ways that someone can have long hair. They can be a woman with long hair or a man with long hair. In the men's restroom line, that's a 1% probability plus a 4% probability, or a 5% probability overall. And you can do the same thing for short hair, 95%. Now, this last concept finishes our foundation. We can get to what we really care about. We know that this person has long hair. What's the probability that they are a man or a woman? This is a conditional probability, but it's the reverse of the one that we know. And we don't know how to answer this yet. So, this is where Thomas Bayes comes in. He noticed something really cool. You can calculate the joint probability that someone is a man and has long hair using the formula we saw before. And you can also calculate the joint probability that someone has long hair and is a man. Now, these are different formulas, but remember, joint probabilities don't care about the order. So these two things are equal, which means the stuff that they're equal to on the other side are also equal to each other. And we can do a little algebraic sleight of hand. And now we have a formula for what we want to know. If someone has long hair, what's the probability that they're a man? And we have this expression to the right. We can genericize that with A's and B's, and now we have Bayes' theorem, one of the top 10 most popular math tattoos of all time. So using this formula, we can go back to the movie theater and plug in what we know. We know that the probability that someone is a man. We know the probability that if they're a man, they have long hair. And we know the conditional probability, the marginal probability that someone has long hair, which is just the probability that someone's a woman with long hair plus the probability that someone's a man with long hair. And we plug all that in, and we can say if someone has long hair at the movie theaters, there is a 7% chance that they are a man. Similarly, 93% chance that they are a woman. Now, if they're in line for the men's restroom, because some of those probabilities change, that conditional probability changes. If someone's in line for the men's restroom and has long hair, there's an 80% chance that they are a man. And this is consistent with what we saw before. We know that there are 4 men and 1 woman for every 100 people in line for the men's restroom that have long hair. So 4 out of 5 long-haired people are men, 80%. It all adds up. So this example shows the mechanics of how to get Bayes' theorem and how it works. In practice, it's usually used a little differently. So to show this, we'll have to do a little bit of a detour and first talk about probability distributions. You could think of probability like a pot with just 1 cup of coffee in it. You can fill up, if you just have 1 cup to fill up, you can fill it all the way to the top. But if you have more than 1 cup, you have to share it around or distribute it. And you can share it in any proportion you want. So for instance, if we're representing the number of men and women at the movies, we could share it 50-50, but it'll always add up to 100%. We could even share it further into different categories. So here we see the joint probabilities of all of our 4 different categories that we were working with. And you can see that this is just another representation of the distribution representation that we were looking at before. Now usually when we look at this, they're side by side, probability instead of percentage, and shown in a histogram like this. It can be really helpful to think of these as beliefs. So for instance, if I flip a coin and hide the result from you, you might half believe it's heads and half believe it's tails until I tell you what it is. If I roll a die and hide the result from you, you might believe about 1/6 that it's a 1 or a 2 or a 3 or 4 or 5 or 6 until I show you the result. So these are what you believe. Probabilities can represent what you believe about something before you measure it. Similarly for Powerball tickets, and even for things that are more complicated, like let's say the height of adults in the United States in centimeters. You might believe that there's a very small chance that they'll be over 210 centimeters and a smallish chance that they're less than 150 centimeters, and then assign various amounts of this belief to all of the ranges in between. It still adds up to 1. It's like a bunch of cups of coffee lined up in a row, and you put a little bit in each one. The cups in the middle have more. And it shows how your belief about some individual is distributed before you've actually measured them. Now you can take these bins and chop them more and more finely, again and again, and if you keep doing this, you can get to something that's actually perfectly smooth. So it's as if you had an infinite number of very tiny cups and you put a tiny bit, infinitesimal amount of coffee in each one. At this point, it's probably no longer helpful to think of it in that terms, but just thinking of it as a continuous distribution, showing for all these heights, where am I placing my bets? What do I believe and how much? So once you have your beliefs, you can use it to answer questions about typical heights, the average, the median value, the most common value, or the mode. Now we'll use this in weighing my dog. I have a Shih Tzu named Reign of Terror. She's a little mischievous, and when we go to the veterinarian, Reign squirms on the scale. So every time we weigh her, we get a different weight. This last time we got 13.9 pounds, 17.5 pounds, and 14.1 pounds. What we want to know is how much Reign weighs. And this will be the basis for a decision. This is important. If her weight has gone up, her food intake will have to go down. And for her, this is a matter of life and death. So we don't want to make the wrong assumption and draw the wrong conclusion. So if you've ever taken a statistics class before, you know you can take these measurements, add them up, get the average, 15.2 pounds. You can calculate the standard deviation of these 3 measurements and also the standard error and come up with a 1.16 pound standard error, which when you show it graphically, this red curve now shows the belief that results from those 3 measurements, the distribution. The peak of that hill is at 15.2 pounds, and 1 standard deviation on that curve is our standard error of 1.2 pounds. So you can see looking at this that yes, it's most likely that she's 15.2 pounds, but there's a lot of that curve that sits outside of the range of 14 to 16. So yeah, she's probably between 14 and 16 pounds, most likely between 13 and 17 pounds, but she might even be lower than 12 and higher than 18. That is a really wide range, and it's not a great basis for making a decision. Now you can see the three measurements there, those three white vertical lines, and you can see why our belief is so dispersed, because those three measurements are pretty dispersed. It's hard to capture all that in one distribution. So let's try it again with Bayes' theorem. So the way we'll do this is, instead of A and B, we'll substitute in W for her actual weight and M for the measurements that we took. Now this term over here, the probability distribution of the actual weight, is our prior. This is what we believe about her weight before we put her on the scale. The probability given a weight of getting certain measurements are the likelihood associated with those measurements. And then the posterior is what we believe about her weight given those measurements. So you can think of this as, we start with a belief, we take some measurements and we update it, and then we have a new belief when we're done. This term on the bottom we're going to ignore for the most part. It'll be a constant, but it's called the marginal likelihood. So we're going to start by not assuming anything about her weight. Could be 1 pound, 10 pounds, 20 pounds, 100 pounds. We're going to let this be uniform, and we're going to let the data speak. So now our formula looks like this. We can further simplify it. And so we want to calculate this. We want to calculate the probability of our measurements occurring given a weight. And we want to do this for all of the possible weights. And then we'll end up with a new distribution, which is our belief. What's the probability of each of those weights occurring given the measurements? So these two things are identical. So let's start, for instance, by assuming, what if she weighed 17 pounds in reality? Now, because our measurement process is very noisy, as we saw, if she weighed 17 pounds, we would expect those measurements to be distributed as shown here. Some would be up way above 18 pounds, some would be down around 14 pounds, where we actually measured, but not very many of them would be. So to calculate now the probability of our measurements occurring, given this weight, we find what the probability of each individual weight is of occurring, and we multiply that times that times that. Now these two are pretty small. When you multiply two small things together, they make something very small. So the probability of her being at 17 pounds is pretty small. We shift our belief over and say, well, what if she was 16 and a half pounds? What if she was 16 pounds? And we recalculate it each time, multiplying all of those actual probabilities together. And then by the time we're done, this is what we've measured at each of those weights. This is the likelihood of each of those occurring. And you can see that the maximum likelihood occurs at 15.2 pounds. And this is commonly called the maximum likelihood estimate, where you start with uniform assumptions on your weight. And it just so happens that the standard error on this is exactly what we calculated before. A very cool connection here. When you take the average and calculate standard deviation and standard error, it gives you the likelihood that you would get by doing Bayes' method and assuming a uniform prior, not assuming anything about what the result's going to be. So, we've already established, though, that that's a really broad result and not helpful. So we need to start over now, and let's start with what we know. So some background information. Rain was 14.2 pounds the last time we went into the vet. And she doesn't seem noticeably more heavy to me. My arm is not that well calibrated, but I'm going to assume that she's within about a pound of where she was before. So I take that prior, and this is the form that it takes. A normal distribution centered on 14.2 pounds, and you can see that most of that bulk is within plus or minus a pound. And it extends a little bit further out. Allow for the possibility that she's actually gained a lot or lost a lot of weight, but probably she's pretty close. This is what I believe before I even put her on the scale. This is the probability, the probability of her being a given weight. So this time we're not neglecting the prior term. We're not setting it constant. We're going to use it. And the way this plays out now is we assume, okay, what if she were 17 pounds? Well, we need to multiply that now by the probability of our prior showing that she's 17 pounds, which actually makes that quite small. Now we calculate and multiply the three probabilities of our measurements occurring. So now we have something small times something very small times something very small. So we get a very small result probability that she actually weighs 17 pounds. And now we repeat this process at 16.5 pounds and 16 pounds and 15.5 pounds and 15 pounds all the way through. And then by the time we're done, we tally up all of those and we get this new posterior distribution. It's normally distributed at about 14.1 pounds, and it has a standard error of less than a pound. You'll notice it's even narrower than our original prior. So we've taken our original belief and we've been able to sharpen it up just a bit. And so incidentally, the peak of this curve is called the maximum a posteriori result. If we had to choose one value to represent our belief, that's not a bad one to choose. And now we compare this with our original estimate. It's labeled non-Bayesian here, but more accurately it could be Bayesian with a uniform prior. You can see that it is much broader, and also the peak of that curve is in an entirely different place. So the answer that we got, it's more confident because it's more centered, and it's probably, based on what we know, closer to being correct. So this is how Bayes' theorem is used most often in data science or in analysis. It's a prior that you then update based on your measurements to sharpen up and get a revised set of beliefs. So there's a lot of times that it makes sense to use Bayesian inference. Sometimes we just know things. Like if we're measuring age, we know that everyone is more than 0 years old. And so we can take that information and build it in, and we can get sharper estimates with fewer measurements. Now, so it should, if you're paying attention, make you a little bit nervous. We humans are actually not always aware of what we believe, and putting it into a mathematical distribution can be very tricky. More importantly, the reason we're measuring something is because we want to learn about it. We want to be able to be surprised by our data. So if we believe something that's not true, it can make it hard or impossible to learn from our data. I like how Mark Twain phrased this. He says, it ain't what you don't know that gets you into trouble, it's what you know for sure that just ain't so. So the way to avoid this pitfall is to always believe things that we think are impossible, at least just a little bit. So by leaving this room for something to be possible, we can do like Sherlock Holmes says, and once you've excluded the impossible, then whatever remains, however improbable, must be the truth. We don't want to exclude the improbable out of hand, because then we're left with nothing. Alice, in a conversation with the Red Queen, summed it up well too. There's no use in trying, she said. One can't believe impossible things. I dare say you haven't had much practice, said the Queen. When I was younger, I always did it for half an hour a day. Why sometimes I've believed as many as 6 impossible things before breakfast. So the secret to using Bayesian inference well is to keep believing impossible things. Thanks for your attention. Here's how you can get in touch with me if you'd like to carry on the conversation. I look forward to talking with you again soon.
You can learn to drive a car by getting the keys, having someone show you how the steering wheel, the gas, and the brakes work. Try it out in a quiet parking lot and then ease yourself onto the open road. And before long, you're able to get yourself to the grocery store and to a friend's house, and you can get done the basics. Now, contrast that with becoming a race car driver. In that case, you want to be able to get as much performance as possible out of your car. And to do that, you need to know how it works down to the nuts and bolts. That's the process of looking under the hood or opening the black box. If you want to get the most out of your tools, then how things work really matters. So to show you what I mean by this, for most of us, beginning machine learning or software engineers, this is what a support vector machine looks like. Here is the black box. You import scikit-learn, queue up a simple example and run it, and you're done. Here are the keys, here's the steering wheel, go. But to get the most out of it, you have to go deeper. My goal in this talk is to walk you through the process of going deeper, but more importantly, to show how any of us can go deep on any subject that we want to master. So as I tackled support vector machines, which were fairly new to me when I started this presentation, the first step I took was to read the scikit-learn documentation. This is what I came across. It's not particularly helpful to me being new to support vector machines. It's a nice, concise summary of the basic principles of how they work, but it doesn't explain it to someone who doesn't already know them well. One thing that the scikit-learn documents did provide was this great diagram showing here 2 different colors of points being separated by a line. That line looks kind of like a road where those 2 lanes are as wide as they can possibly get before they start touching data points. This was helpful. My next step was to go find a nice tutorial and read it. I found one that was highly recommended and started reading through it. And I saw definitions and tables and equations and graphs and diagrams and plots, and very soon got very overwhelmed, and there were theorems, for God's sake. And I felt strongly that it was probably important stuff, but it was not very accessible to someone who is new to the topic. So I took a step back, I set that aside, and I went to YouTube. And I pulled up some of the most popular videos on support vector machines, and in the course of doing this, saw multiple explanations of what they are, what they're used for, how to visualize them, how the math underneath them works. And the principles finally started to click. They began becoming clear in my brain. Following this, I went and found some more blog posts, again from a variety of posters, each with their own way of visualizing how they work, of explaining the principles behind it, and now the equations and the math and the definitions started to make a little sense. Enough so that I, in the next step, started to try to explain it to myself. And the way I do this is by drawing pictures. And so I started illustrating some of these concepts in a way that would make sense to me in my brain. Now that the ideas underneath support vector machines, at this stage, they're crystals, they're nuggets, but they're a scaffold, but they're not fleshed out. So to do this, I find it very helpful to choose a toy example. This is a bit of an art, it's trial and error, but finding an example that's simple enough that you understand it completely and you know exactly how it should work, but it's just complicated enough to illustrate the principle. So for this one, I settled on fruit. So imagine that we have fruit. It can either be small or large or yellow or purple. Now, any small fruit is a plum. If it's yellow, it's not yet ripe, but if it's purple, it's ripe and good to eat. Any large fruit is a peach. If it's yellow, it's great to eat, but if it's purple, it's rotten. You don't want to eat it. So in this example, we have in the world of peaches, there's a size axis and a color axis, and you can see the good things to eat are at the upper left and the lower right. Now, in this example, once you have this example, if you can get it to where you can explain it to, roughly like a 12-year-old, a 6th grader, which means that you use words and ideas that are common, no jargon, or if you do use a jargon term, you explain it thoroughly. So here's my attempt to do that for support vector machines. So imagine you have peaches, and they can be any color between yellow and purple, and you would like to figure out which ones are good to eat. You'd like to know, in fact, if you get a new peach based on its color, whether you should eat it or not. So what you do is you get a bunch of peaches and you grab one and you try it. You get one that happens to be yellow, you taste it, it's good. So you make a green circle and put it at the point that represents its color. You grab another one that's pretty purple and you taste it and it's nasty, it's rotten. So you put a black X at the point that represents its color. And you do this again for a few more peaches, some yellow ones, some purple ones, some ones in between. And before long, you have a data set that looks like this. The green circles all show good peaches, the black X's show bad peaches. Now that you have all this data, you would like to make a prediction. Based on a peach's color, do you expect it to be good to eat? Support vector machines allow you to do this. And what they do when you have two groups of data is they come and they put what looks like a road in between them. There's a dotted center line and then two lanes, and it tries to make that road as wide as it can possibly get until the outside of those two lanes bump up against your two data sets. The center line is the divider between the two groups. Anything to the left of that will be assumed to be good to eat. Anything to the right of that will be assumed to be bad to eat. And the lanes on either side are called margins, for lack of a better term. Now, imagine though that in this set of peaches, this can be trickier. What if you have some that don't really fall with the group? You get some yellow peaches that just don't taste right, or you get a purple peach that for some reason tastes amazing. Now the data set, there's nowhere you can draw a line that separates the green circles from the black X's. But what you can do is still create a dividing line with its margins, but any data point that is on the wrong side of its margin gets a penalty based on how far it is over. And so you can move the position of this dividing line and the width of its margins to take that penalty and add that penalty in and still make that as small as you possibly can. So you can still use support vector machines in cases where your data isn't completely separate. The fancy term for that is linearly separable. Just means you can't separate it with a line. So it can handle non-linearly separable data. Now let's look at a different case. Instead of just peaches, we have peaches and plums. The good ones, we either want to eat yellow peaches or purple plums. A yellow plum isn't ripe and a purple peach is rotten. So we can do the same thing in this world. We try a bunch of fruit of different sizes and different colors. We find that the yellow peaches are delicious. We find that the purple plums are delicious, but the yellow plums are terrible and the black peaches, the purple peaches are terrible. So we end up with a data set that looks like this. The challenge now is that if we try to draw a line to separate these out, it's not just that a few data points are going to be a little bit off. There's a whole chunk of our data that we're missing. We're not capturing it well. So this data is obviously not linearly separable. To help us visualize this, I went and took it into Python and made a different visualization of it. But it's the same thing, green circles and black X's. We'd like to try to separate them. And In this case, we can't with a line. Now, support vector machines have an answer to this. What you do is you imagine that all of these data points are not on a flat plane, but they're on a sheet of rubber. And you can pick that sheet of rubber up and you can stretch it and bend it and warp it however you want. And you can probably visualize here that if you take that and bend it just right and slice it, you can separate out the good to eat fruit from the bad to eat fruit. And this is exactly how you would do it. If you can now, with a single straight slice, you can separate these things out nicely. This trick of bending your sheet of paper, of warping it, is called the kernel trick. And it refers to how it's calculated. But in practice, all you need to know is you can take this space that your data is in, this paper that it's on, and twist it and bend it however you want. You can take and hold down the middle and pull up all four edges. Or you can pull up all four edges and pull up the middle and leave a little ring low around the middle, or low around the center. Or you can take it and pull it up and pull it down and make it like an egg crate so that you can capture really irregularly spaced data, and with a single slice, you can separate it all out from each other. So the kernel trick is really powerful. And in fact, there is no limit to what you can do with this space to bend it. To illustrate another way that it's powerful, let's consider a slightly different problem. Now we have fruit. We don't care about the size, but we have 5 different colors. Green peaches are unripe. They're not yet ripe. Yellow peaches are ripe, so they're good. Orange fruit is an unripe plum, and a purple is a ripe plum. And then a black fruit is rotten. So the good ones to eat are the yellow peaches and the purple plums. Any other color is bad to eat. Now you can see that all of this data is just on one line, but there's no nice way to slice it to separate the green circles from the black X's. Now we can use the kernel trick. We can take that line essentially and bend it however we want. One way to do that is to just make a single bend in it, like a smiley face. And you can see that, great, we bent it, but still those circles and X's are not laid out so that with a single cut, we can separate them from each other. Now, the cool part about the support vector machine kernel trick is that you can come back and bend your space again in a different direction. So this represents a 2-dimensional kernel. And now it's not too hard to see that with the right slice, you can come in there with the plane and separate out those green circles from those black X's. Now, if you look carefully, you'll notice that this slice is actually not exactly the one you'd want. It kind of misses, but you can imagine where it would go to separate those out. So here we did 2 different warpings. We took our line and we bent it one direction, and then we bent it another direction. Because of the math, it's a little bit mind-blowing, but you can actually take whatever space your data is in, and you can bend it in an infinite number of directions to make it so that you can slice it and separate out your 2 groups of data. So that is pretty powerful stuff. This is what support vector machines do. They take and find the best slice that separates out 2 groups of data, and if your data is hard to separate, you can warp and twist your space until you find a way to separate it. Okay, so that's the explanation. Now comes the most important part. In addition to understanding the strengths of a method, you have to understand its weaknesses if you're going to use it well and push it to its limits. So, with support vector machines, issues include if you have data with lots of error. So if you notice, any time that we're finding a slice between 2 groups of data, the location of that slice depends almost entirely on the very nearest data points. The other ones, it doesn't matter if they're close to the margin or miles away from the margin. It's those nearest data points that determine exactly where that margin is going to be. And if each of those has a lot of error associated with it, then that error gets a really loud vote, more so than most of your data. So that is an issue. Another way that it can break is if you choose the wrong kernel. If you look back at the original data set where we were bending our paper like a sheet of rubber, if we bent it the wrong way, we would not be able to separate out our data sets. We had to bend it just the right way. That's choosing the right kernel. And the act of choosing the right kernel is an art. And it's done by trial and error and, after a while, by experience. And then finally, large data sets can break support vector machines. Calculating the kernel, some kernels especially, can be very expensive, take a lot of computing power. And so if you're not dealing with just hundreds of data points, but billions, then the amount of time to calculate those is prohibitive. So with large data sets, you have to stick with linearly separable problems. So you have to go back and hand engineer features that help your data get separated out. Help it so you can separate it with a straight line, single cut. So each of these requires a human in the loop to determine when it's a problem and to work around it. This is important to know. This means that support vector machines are powerful, but to get the most out of them, you need someone who has used them quite a bit and understands them well. This doesn't mean that they can't be used, but this is important to know when you're deciding what method to use on your problem. Now, taking a step back, that was a quick walk through support vector machines. Hopefully you understand it now a little bit better than you did before if you were new to it. And now going into another project, you know what you need to do to make good use of it. A comment on the process. We went through this together. There was no formal education, no coursework, no textbook, no professor, no permission granted, no special libraries, nothing purchased. This is all information that's out there. This is something that you can do with any tool you want. You can take and open the box and see what's inside. You can lift up the hood and you can see what the pieces are and how they work together. It's not an easy process, and sometimes it's quite painful, but it is something that you have at your disposal. And it's something that, in the cases of my key tools, I have found it very worth my while. So I encourage you, when you have something that you think you might need to use heavily, take some time, open the box, figure out how it works so you go from a grocery getter to a really high-performing race car. Thank you.
Hello, welcome to How Convolutional Neural Networks Work. Convolutional neural networks, or ConvNets or CNNs, can do some pretty cool things. If you feed them a bunch of pictures of faces, for instance, they'll learn some basic things like edges and dots, bright spots, dark spots. And then because they're a multi-layer neural network, that's what gets learned in the first layer. The second layer are things that are recognizable as eyes, noses, mouths. And the third layer are things that look like faces. Similarly, if you feed it a bunch of images of cars, down at the lowest layer, you'll get things, again, that look like edges. And then higher up, you get things that look like tires and wheel wells and hoods. And at a level above that, things that are clearly identifiable as cars. CNNs can even learn to play video games by forming patterns of the pixels as they appear on the screen and learning what is the best action to take when it sees a certain pattern. A CNN can learn to play video games, in some cases, far better than a human ever could. Not only that, if you take a couple of CNNs and have them set to watching YouTube videos, one can learn objects by, again, picking out patterns, and the other one can learn types of grasps. This then, coupled with some other execution software, can let a robot learn to cook just by watching YouTube. So there's no doubt CNNs are powerful. Usually when we talk about them, we do so in the same way we might talk about magic. But they're not magic. What they do is based on some pretty basic ideas applied in a clever way. So to illustrate these, we'll talk about a very simple toy convolutional neural network. What this one does is takes in an image, a two-dimensional array of pixels. You can think of it as a checkerboard, and each square on the checkerboard is either light or dark. And then by looking at that, the CNN decides whether it's a picture of an X or of an O. So for instance, on top there, we see an image with an X drawn in white pixels on a black background. And we would like to identify this as an X. And the O, we'd like to identify as an O. So how a CNN does this has several steps in it. What makes it tricky is that the X is not exactly the same every time. The X or the O can be shifted, it can be bigger or smaller, it can be rotated a little bit, thicker or thinner, and in every case we would still like to identify whether it's an X or an O. Now the reason that this is challenging is because for us, deciding whether these two things are similar is straightforward. We don't even have to think about it. For a computer, it's very hard. What a computer sees is this checkerboard, this two-dimensional array, as a bunch of numbers, ones and minus ones. A 1 is a bright pixel, a minus 1 is a black pixel, and what it can do is go through pixel by pixel and compare whether they match or not. So to a computer, it looks like there are a lot of pixels that match, but some that don't, quite a few that don't actually. And so it might look at this and say, I'm really not sure whether these are the same. And so it would, because a computer is so literal, it would say, uncertain. I can't say that they're equal. Now, one of the tricks that convolutional neural networks use is to match parts of the image rather than the whole thing. So if you break it down into its smaller parts or features, then it becomes much more clear whether these two things are similar. So examples of these little features are little mini images. In this case, just 3 pixels by 3 pixels. The one on the left is a diagonal line slanting downward from left to right. The one on the right is also a diagonal line slanting in the other direction. And the one in the middle is a little X. These are little pieces of the bigger image. And you can see as we go through, if you choose the right feature and put it in the right place, it matches the image exactly. So okay, we have the bits and pieces. Now, to take a step deeper, the math behind matching these is called filtering. And the way this is done is a feature is lined up with the little patch of the image, and then one by one, the pixels are compared. They're multiplied by each other, and then added up and divided by the total number of pixels. So to step through this, to see why it makes sense to do this, you can see starting in the upper left-hand pixel in both the feature and the image patch, multiplying a 1 by a 1 gives you a 1. And we can keep track of that by putting that in the position of the pixel that we're comparing. We step to the next one, minus 1 times minus 1 is also a 1. And we continue to step through pixel by pixel, multiplying them all by each other, and because they're always the same, the answer is always 1. When we're done, we take all these 1s and add them up and divide by 9, and the answer is 1. So now we want to keep track of where that feature was in the image, and we put a 1 there. Say, when we put the feature here, we get a match of 1. That is filtering. Now we can take that same feature and move it to another position and perform the filtering again. And we start with the same pattern. The first pixel matches, the second pixel matches, the third pixel does not match. Minus 1 times 1 equals minus 1. So we record that in our results. And we go through and do that through the rest of the image patch. And when we're done, we notice we have 2 minus 1s this time. So we add up all the pixels, which add up to 5, divide by 9, and we get a 0.55. So this is very different than our 1. And we can record the 0.55 in that position, where we were, where it occurred. So by moving our filter around to different places in the image, we actually find different values for how well that filter matches or how well that feature is represented at that position. So this becomes a map of where the feature occurs. By moving it around to every possible position, we do convolution. That's just the repeated application of this feature, this filter, over and over again. And what we get is a nice map across the whole image of where this feature occurs. And if we look at it, it makes sense. This feature is a diagonal line slanting downward, left to right, which matches the downward, left to right diagonal of the x. So if we look at our filtered image, we see that all of the high numbers, 1s and 0.77s, are all right along that diagonal. That suggests that that feature matches along that diagonal much better than it does elsewhere in the image. To use a shorthand notation here, we'll do a little X with a circle in it to represent convolution, the act of trying every possible match. And we repeat that with other features. We can repeat that with our X filter in the middle and with our upward slanting diagonal line in the bottom. And in each case, the map that we get of where that feature occurs is consistent with what we would expect based on what we know about the X and about where our features match. This act of convolving an image with a bunch of filters, a bunch of features, and creating a stack of filtered images is we'll call a convolution layer. A layer because it's an operation that we can stack with others, as we'll show in a minute. In convolution, one image becomes a stack of filtered images. We get as many filtered images out as we have filters. So convolution layer is one trick that we have. The next big trick that we have is called pooling. This is how we shrink the image stack. And this is pretty straightforward. We start with the window size, usually 2 by 2 pixels or 3 by 3 pixels, and a stride, usually 2 pixels. Just in practice, these work best. And then we take that window and walk it in strides across each of the filtered images. From each window, we take the maximum value. So to illustrate this, we start with our first filtered image. We have our 2 pixel by 2 pixel window. Within that pixel, the maximum value is 1. So we track that and then move to our stride of 2 pixels. We move 2 pixels to the right and repeat. Out of that window, the maximum value is 0.33, etc., 0.55. And when we get to the end, we have to be creative. We don't have all the pixels representative, so we take the max of what's there. And we continue doing this across the whole image. And when we're done, what we end up with is a similar pattern, but smaller. We can still see our high values are all on the diagonal, but instead of 7 by 7 pixels in our filtered image, we have a 4 by 4 pixel image. So it's half as big as it was about. This makes a lot of sense to do if you can imagine if instead of starting with a 9 by 9 pixel image, we had started with a 9,000 by 9,000 pixel image. Shrinking it is convenient for working with it. Makes it smaller. The other thing it does is pooling doesn't care where in that window that maximum value occurs. So that makes it a little less sensitive to position. And the way this plays out is that if you're looking for a particular feature in an image, it can be a little to the left, a little to the right, maybe a little rotated, and it'll still get picked up. So we do max pooling with all of our our stack of filtered images and get, in every case, smaller set of filtered images. Now, that's our second trick. Third trick, normalization. This is just a step to keep the math from blowing up and keep it from going to zero. All you do here is everywhere in your image that there is a negative value, change it to zero. So for instance, if we're looking back at our filtered image, we have these what are called rectified linear units. That's the little computational unit that does this. But all it does is steps through everywhere there's a negative value, change it to zero. Another negative value, change it to zero. By the time you're done, you have a very similar looking image, except there's no negative values. They're just zeros. And we do this with all of our images, and this becomes another type of layer. So in a rectified linear unit layer, a stack of images becomes a stack of images with no negative values. Now, what's really fun, the magic starts to happen here when we take these layers, convolution layers, rectified linear unit layers, and pooling layers, and we stack them up so that the output of one becomes the input of the next. You'll notice that what goes into each of these and what comes out of these looks like an array of pixels, or an array of pixels. And because of that, we can stack them nicely. We can use the output of one for the input of the next. And by stacking them, we get these operations building on top of each other. What's more, we can repeat the stacks. We can do deep stacking. You can imagine making a sandwich that is not just one patty and one slice of cheese and one lettuce and one tomato, but a whole bunch of layers, double, triple, quadruple deckers, as many times as you want. Each time, the image gets more filtered as it goes through convolution layers, and it gets smaller as it goes through pooling layers. Now, the final layer in our toolbox is called a fully connected layer. Here, every value gets a vote on what the answer is going to be. So we take our now much filtered and much reduced in size stack of images. We break them out, we just rearrange and put them into a single list because it's easier to visualize that way. And then each of those connects to one of our answers that we're going to vote for. When we feed this an X, there will be certain values here that tend to be high. They tend to predict very strongly that this is going to be an X. They get a lot of vote for the X outcome. Similarly, when we feed in a picture of an O to our convolutional neural network, there are certain values here at the end that tend to be very high and tend to predict strongly when we're going to have an O at the end. So they get a lot of weight, a strong vote for the O category. Now when we get a new input and we don't know what it is and we want to decide, the way this works is the input goes through all of our convolutional, our rectified linear unit, our pooling layers, and comes out to the end here. We get a series of votes, and then based on the weights that each value gets to vote with, we get a nice average vote at the end. In this case, this particular set of inputs votes for an X with a strength of 0.92 and an O with a strength of 0.51. So here, definitely X is the winner, and so the neural network would categorize this input as an X. So in a fully connected layer, a list of feature values becomes a list of votes. Now, again, what's cool here is that a list of votes looks a whole lot like a list of feature values, so you can use the output of one for the input of the next. And so you can have intermediate categories that aren't your final votes, or sometimes these are called hidden units in a neural network. And you can stack as many of these together as you want also. But in the end, they all end up voting for an X or an O, and whoever gets the most votes wins. So if we put this all together, then a two-dimensional array of pixels in results in a set of votes for a category out at the far end. So there are some things that we have glossed over here. You might be asking yourself where all of the magic numbers come from. Things that I pulled out of thin air include the features in the convolutional layers, those convenient 3 pixel by 3 pixel diagonal lines of the X. Also, the voting weights in the fully connected layers. I really waved my hands about how those are obtained. In all these cases, the answer is the same. There is a trick called backpropagation. All of these are learned. You don't have to know them. You don't have to guess them. The deep neural network does this on its own. So the underlying principle behind backpropagation is that the error in the final answer is used to determine how much the network adjusts and changes. So in this case, if we knew we were putting in an X, and we got a 0.92 vote for an X, and that would be an error of 0.08, and we got a 0.51 vote for an O, we know that that would be an error of 0.49, actually an error of 0.51 because it should be 0. Then if we add all that up, we get an error of what should be 0.59. So what happens with this error signal is it helps drive a process called gradient descent. If there is another bit of something that is pretty special sauce to deep neural networks, it is the ability to do gradient descent. So for each of these magic numbers, each of the feature pixels, each voting weight, they're adjusted up and down by a very small amount to see how the error changes. The amount that they're adjusted is determined by how big the error is. Large error, they're adjusted a lot. Small error, just a tiny bit. No error, they're not adjusted at all. You have the right answer, stop messing with it. As they're adjusted, you can think of that as sliding a ball slightly to the left and slightly to the right on a hill. You want to find the direction where it goes downhill. You want to go down that slope, down that gradient to find the very bottom, because the bottom is where you have the very least error. That's your happy place. So after sliding it to the left and to the right, you find the downhill direction and you leave it there. Doing that many times over lots of iterations, lots of steps, helps all of these values across all the features and all of the weights settle in to what's called a minimum. And at that point, the network is performing as well as it possibly can. If it adjusts any of those a little bit, its error will go up. Now, there are some things called hyperparameters, and these are knobs that the designer gets to turn, decisions the designer gets to make. These are not learned automatically. In convolution, figuring out how many features should be used, how big those features should be, how many pixels on a side. In the pooling layers, choosing the window size and the window stride. And in fully connected layers, choosing the number of hidden neurons, intermediate neurons. All of these things are decisions that the designer gets to make. Right now, there are some common practices that tend to work better than others, but there is no principled way. There's no hard and fast rules for the right way to do this. And in fact, a lot of the advances in convolutional neural networks are in getting combinations of these that work really well. Now, in addition to this, there are other decisions the designer gets to make, like how many of each type of layer and in what order. And for those that really like to go off the rails, can we design new types of layers entirely and slip them in there and get new fun behaviors? These are all things that people are playing with to try to eke out more performance and address stickier problems with CNNs. Now, what's really cool about these, we've been talking about images, but you can use any two-dimensional, or even for that matter, 3- or 4-dimensional data. But what's important is that in your data, things closer together are more closely related than things far away. What I mean by that is if you look at an image, 2 rows of pixels or 2 columns of pixels are right next to each other, they're more closely related than rows or columns that are far away. Now what you can do is you can take something like sound and you can chop it up into little time steps, and for each piece of time, the time step right before it and right after is more closely related than time steps that are far away, and the order matters. You can also chop it up into different frequency bands. Bass, mid-range, treble, you can slice it a whole lot more finely than that. And again, those frequency bands are the ones closer together, are more closely related, and you can't rearrange them. The order matters. Once you do this with sound, it looks like a picture. It looks like an image, and you can use convolutional neural networks with them. You can do something similar with text, where the position in the sentence becomes the column, and the row is words in a dictionary. In this case, it's hard to argue whether order matters. That order matters. It's hard to argue that words in a dictionary are, that some are more closely related than others in all cases. And so the trick here is to take a window that spans the entire column, top to bottom, and then slide it left to right. That way it captures all of the words, but it only captures a few positions in the sentence at a time. Now, the other side of this limitation of convolutional neural networks is that they're really designed to capture local spatial patterns. Spatial in the sense of things that are next to each other matter quite a bit. So if the data can't be made to look like an image, then they're not as useful. So an example of this is, say, some customer data. If I have each row is a separate customer, each column is a separate piece of information about that customer, such as their name, their address, what they bought, what websites they visited, then this doesn't so much look like a picture. I can take and rearrange those columns and rearrange those rows, and this still means the same thing. It's still equally easy to interpret. If I were to take an image and rearrange the columns and rearrange the rows, it would result in a scramble of pixels, and it would be difficult or impossible to say what the image was of. There I would lose a lot of information. So as a rule of thumb, if your data is just as useful after swapping out any of the columns for each other, then you can't use convolutional neural networks. So the take home is that convolutional neural networks are great at finding patterns and using them to classify images. If you can make your problem look like finding cats on the internet, then they're a huge asset. If you'd like to continue your study of CNN, I would recommend looking at the notes from the Stanford Computer Science 231 course from Justin Johnson and Andre Karpathy. Also, checking out the writings of Christopher Olah. He's an exceptionally clear writer. And feel free to check out another presentation that I did, Deep Learning Demystified, talking about some of the properties of deep neural networks in general for someone who is new to the topic. There are, if you'd like to dig even deeper and play with some of these, there's a variety of toolkits. They each have their strengths and weaknesses. I invite you to dig deep into them and learn all about them. Thanks for listening. Feel free to connect with me online, and I would love to follow up with you.
Neural networks are good for learning lots of different types of patterns. To give an example of how this would work, imagine you had a 4-pixel camera. So not 4 megapixels, but just 4 pixels, and it was only black and white. And you wanted to go around and take pictures of things and determine automatically then
whether these pictures were of a solid all white or all dark image, a vertical line or a diagonal line or a horizontal line. This is tricky because you can't do this with simple rules about the brightness of the pixels. Both of these are horizontal lines, but if you tried to make a rule about which pixel was bright and which was dark, you wouldn't be able to do it. So to do this with the neural network, you start by taking all of your inputs, in this case our 4 pixels, and you break them out into input neurons. And you assign a number to each of these depending on the brightness or darkness of the pixel. +1 is all the way white, -1 is all the way black, and then gray is 0, right in the middle. So these values, once you have them broken out and listed like this on the input neurons, it's also called the input vector or array. It's just a list of numbers that represents your inputs right now. It's a useful notion to think about the receptive field of a neuron. All this means is what set of inputs makes the value of this neuron as high as it can possibly be. For input neurons, this is pretty easy. Each one is associated with just one pixel, and when that pixel is all the way white, the value of that input neuron is as high as it can go. The black and white checkered areas show pixels that an input neuron doesn't care about. If they're all the way white or all the way black, it still doesn't affect the value of that input neuron at all. Now, to build a neural network, we create a neuron. The first thing this does is it adds up all of the values of the input neurons. So in this case, if we add up all of those values, we get a 0.5. Now to complicate things just a little bit, each of the connections are weighted, meaning they're multiplied by a number. That number can be 1 or -1 or anything in between. So for instance, if something has a weight of -1, it's multiplied and you get the negative of it, and that's added in. If something has a weight of 0, then it's effectively ignored. So here's what those weighted connections might look like. And you'll notice that after the values of the input neurons are weighted and added, the final value is completely different. Graphically, it's convenient to represent these weights as white links being positive weights, black links being negative weights, and the thickness of the line is roughly proportional to the magnitude of the weight. Then, after you add the weighted input neurons, they get squashed. And I'll show you what that means. You have a sigmoid squashing function. Sigmoid just means S-shaped. And what this does is you put a value in, let's say 0.5, and you run a vertical line up to your sigmoid and then a horizontal line over from where it crosses. And then where that hits the y-axis, that's the output of your function. So in this case, slightly less than 0.5. It's pretty close. As your input number gets larger, your output number also gets larger but more slowly. And eventually, no matter how big the number you put in, the answer is always less than 1. Similarly, when you go negative, the answer is always greater than -1. So this ensures that that neuron's value never gets outside of the range of +1 to -1, which is helpful for keeping the computations in the neural network bounded and stable. So after you sum the weighted values of the neurons and squash the result, you get the output. In this case, 0.746. That is a neuron. So we can collapse all that down, and this is a neuron that does a weighted sum and squash the result. And now instead of just one of those, assume you have a whole bunch. There are 4 shown here, but there could be 400 or 4 million. Now to keep our picture clear,
we'll assume for now that the weights are either +1, white lines, -1, black lines, or 0, in which case they're missing entirely. But in actuality, all of these neurons that we created are each attached to all of the input neurons, and they all have some weight between -1 and +1. When we create this first layer of our neural network, the receptive fields get more complex. For instance, here, each of those end up combining 2 of our input neurons. And so the value, the receptive field, the pixel values that make that first layer neuron as large as it can possibly be, look now like pairs of pixels, either all white or a mixture of white and black, depending on the weights. So for instance, this neuron here is attached to this input pixel, which is upper left, and this input pixel, which is lower left, and both of those weights are positive. So it combines the 2 of those, and that's its receptive field, the receptive field of this one plus the receptive field of this one. However, if we look at this neuron, it combines this pixel, upper right, and this pixel, lower right. It has a weight of -1 for the lower right pixel, so that means it's most active when this pixel is black. So here is its receptive field. Now, because we were careful of how we created that first layer, its values look a lot like input values. And we can turn right around and create another layer on top of it the exact same way, with the output of one layer being the input to the next layer. And we can repeat this 3 times or 7 times or 700 times for additional layers. Each time the receptive fields get even more complex. So you can see here, using the same logic, now they cover all of the pixels and more special arrangement of which are black and which are white. We can create another layer. Again, all of these neurons in one layer are connected to all of the neurons in the previous layer, but we're assuming here that most of those weights are 0 and not shown. It's not generally the case. So just to mix things up, we'll create a new layer, but if you notice, our squashing function isn't there anymore. We have something new called a rectified linear unit. This is another popular neuron type. So you do your weighted sum of all your inputs, and instead of squashing, you do rectified linear units. You rectify it. So if it is negative, you make the value 0. If it's positive, you keep the value. This is obviously very easy to compute, and it turns out to have very nice stability properties for neural networks as well in practice. So after we do this, because some of our weights are positive and some are negative, connecting to those rectified linear units, we get receptive fields and their opposites. If you look at the patterns there. And then finally, when we've created as many layers with as many neurons as we want, we create an output layer. Here, we have 4 outputs that we're interested in. Is the image solid, vertical, diagonal, or horizontal? So to walk through an example here of how this would work, let's say we start with this input image shown on the left. Dark pixels on top, white on the bottom. As we propagate that to our input layer, this is what those values would look like. The top pixels, the bottom pixels. As we move that to our first layer, we can see the combination of a dark pixel and a light pixel summed together get us 0, gray. Whereas down here we have the combination of a dark pixel plus a light pixel with a negative weight. So that gets us a value of -1 there. which makes sense because if we look at the receptive field here, upper left pixel white, lower left pixel black, it's the exact opposite of the input that we're getting. And so we would expect its value to be as low as possible, -1. As we move to the next layer, we see the same types of things, combining zeros to get zeros, combining a negative and a negative with a negative weight, which makes a positive, to get a 0. And here we have combining two negatives to get a negative. So again, you'll notice the receptive field of this is exactly the inverse of our input. So it makes sense that its weight would be negative, or its value would be negative. And we move to the next layer. All of these, of course, these zeros propagate forward. Here, this is a negative, has a negative value, and it has a positive weight. So it just moves straight forward. Because we have a rectified linear unit, negative values become 0. So now it is 0 again too, but this one gets rectified and becomes positive. Negative times the negative is positive. And so when we finally get to the output, we can see they're all 0 except for this horizontal, which is positive, and that's the answer. Our neural network said this is an image of a horizontal line. Now, neural networks usually aren't that good, not that clean. So there's a notion of, with an input, what is truth? In this case, the truth is this has a 0 for all of these values, but a 1 for horizontal. It's not solid, it's not vertical, it's not diagonal. Yes, it is horizontal. An arbitrary neural network will give answers that are not exactly truth. They might be off by a little or a lot. And then the error is the magnitude of the difference between the truth and the answer given. And you can add all these up to get the total error for the neural network. So the whole idea with learning and training is to adjust the weights to make the error as low as possible. So the way this is done is we put an image in, we calculate the error at the end, then we look for how to adjust those weights higher or lower to either make that error go up or down. And we, of course, adjust the weights in the way, then make the error go down. Now, the problem with doing this is each time we go back and calculate the error, we have to multiply all of those weights by all of the neuron values at each layer. And we have to do that again and again once for each weight. This takes forever in computing terms, on a computing scale, and so it's not a practical way to train a big neural network. You can imagine instead of just rolling down to the bottom of a simple valley, we have a very high dimensional valley, and we have to find our way down. And because there are so many dimensions, one for each of these weights, that the computation just becomes prohibitively expensive. Luckily, there was an insight that lets us do this in a very reasonable time. And that's that if we're careful about how we design our neural network, we can calculate the slope directly, the gradient. We can figure out the direction that we need to adjust the weight without going all the way back through our neural network and recalculating. So just to review, the slope that we're talking about is when we make a change in weight, the error will change a little bit. And that relation of the change in weight to the change in error is the slope. Mathematically, there are several ways to write this. We'll favor the one on the bottom. It's technically most correct. We'll call it DEDW for shorthand. Every time you see it, just think the change in error when I change a weight, or the change in the thing on the top when I change the thing on the bottom. This does get into a little bit of calculus. We do take derivatives. That's how we calculate slope. If it's new to you, I strongly recommend a good semester of calculus just because the concepts are so universal. And a lot of them have very nice physical interpretations, which I find very appealing.
But don't worry, otherwise just gloss over this and pay attention to the rest, and you'll get a general sense for how this works. So in this case, if we change the weight by +1, the error changes by -2, which gives us a slope of -2. That tells us the direction that we should adjust our weight and how much we should adjust it to bring the error down. Now to do this, you have to know what your error function is. So assume we had an error function that was the square of the weight, and you can see that our weight is right at -1. So the first thing we do is we take the derivative, change in error, divided by change in weight, dE dw. The derivative of weight squared is 2 times the weight. And so we plug in our weight of -1, and we get a slope, dE dw, of -2. Now the other trick that lets us do this with deep neural networks is chaining. And to show you how this works, imagine a very simple trivial neural network with just one hidden layer, one input layer, one output layer, and one weight connecting each of them. So it's obvious to see that the value y is just the value x times the weight connecting them, w1. So if we change w1 a little bit, we just take the derivative of y with respect to w1, and we get x. The slope is x. If I change w1 by a little bit, then y will change by x times the size of that adjustment. Similarly, for the next step, we can see that e is just the value y times the weight w2. And so when we calculate dE dy, it's just w2. Because this network is so simple, we can calculate from one end to the other. X times w1 times w2 is the error e. And so if we want to calculate how much will the error change if I change w1, we just take the derivative of that with respect to w1 and get x times w2. So this illustrates, you can see here now, that what we just calculated is actually the product of our first derivative that we took, the dy dw1, times the derivative for the next step, dE dy, multiplied together. This is chaining. You can calculate the slope of each tiny step and then multiply all of those together to get the slope of the full chain, the derivative of the full chain. So in a deeper neural network, what this would look like is if I want to know how much the error will change if I adjust a weight that's deep in the network, I just calculate the derivative of each tiny little step all the way back to the weight that I'm trying to calculate, and then multiply them all together. This computationally is many, many times cheaper than what we had to do before of recalculating the error for the whole neural network for every weight. Now, in the neural network that we've created, there are several types of backpropagation we have to do. There are several operations we have to do. For each one of those, we have to be able to calculate the slope. So for the first one is just a weighted connection between two neurons, A and B. So let's assume we know the change in error with respect to B. We want to know the change in error with respect to A. To get there, we need to know dB dA. So to get that, we just write the relationship between B and A, take the derivative of B with respect to A, we get the weight, W, and now we know how to make that step. We know how to do that little nugget of backpropagation. Another element that we've seen is sums. All of our neurons sum up a lot of inputs. To take this backpropagation step, we do the same thing. We write our expression, and then we take the derivative of our endpoint, z, with respect to our step that we're propagating to, a, and dz dA in this case is just 1, which makes sense. If we have a sum of a whole bunch of elements, we increase one of those elements by 1, we expect the sum to increase by 1. That's the definition of a slope of 1. One-to-one relation there. Another element that we have that we need to be able to backpropagate is the sigmoid function. So this one's a little bit more interesting mathematically. We'll just write it shorthand like this, the sigma function. It is entirely feasible to go through and take the derivative of this analytically and calculate it. It just so happens that this function has a nice property that to get its derivative, you just multiply it by 1 minus itself. So this is very straightforward to calculate. Another element that we've used is the rectified linear unit. Again, to figure out how to backpropagate this, we just write out the relation. B is equal to A if A is positive, otherwise it's 0. And piecewise, for each of those, we take the derivative. So dB dA is either 1 if A is positive or 0. And so with all of these little backpropagation steps and the ability to chain them together, we can calculate the effect of adjusting any given weight on the error for any given input. And so to train, then, we start with a fully connected network. We don't know what any of these weights should be, and so we assign them all random values. We create a completely arbitrary random neural network. We put in an input that we know the answer to. We know whether it's solid, vertical, diagonal, or horizontal, so we know what truth should be, and so we can calculate the error. Then we run it through, calculate the error, and using backpropagation, go through and adjust all of those weights a tiny bit in the right direction. And then we do that again with another input, and again with another input for, if we can get away with it, many thousands or even millions of times. And eventually, all of those weights will gravitate, they'll roll down that many-dimensional valley to a nice low spot in the bottom where it performs really well and does pretty close to truth on most of the images. If we're really lucky, it'll look like what we started with intuitively understandable receptive fields for those neurons and a relatively sparse representation, meaning that most of the weights are small or close to 0. And it doesn't always turn out that way, but what we are guaranteed is that it'll find a pretty good representation of the best that it can do adjusting those weights to get as close as possible to the right answer for all of the inputs. So what we've covered is just a very basic introduction to the principles behind neural networks. I haven't told you quite enough to be able to go out and build one of your own, but if you're feeling motivated to do so, I highly encourage it. Here are a few resources that you'll find useful. You'll want to go and learn about bias neurons. Dropout is a useful training tool. There are several resources available from Andrej Karpathy, who is an expert in neural networks and great at teaching about it. Also, there's a fantastic article called The Black Magic of Deep Learning that just has a bunch of practical from the trenches tips on how to get them working well. If you found this useful, I highly encourage you to visit my blog and check out several other How It Works style posts. And the links for these slides you can get as well to use however you like. There's also a link to them down in the comments section. Thanks for listening.
Applications of machine learning have gotten a lot of traction in the last few years. There's a couple of big categories that have had wins. One is identifying pictures, the equivalent of finding cats on the internet, and any problem that can be made to look like that. And the other is sequence-to-sequence translation. This can be speech to text or one language to another. Most of the former are done with convolutional neural networks. Most of the latter are done with recurrent neural networks, particularly long short-term memory. To give an example of how long short-term memory works, we will consider the question of what's for dinner.
Let's say for a minute that you are a very lucky apartment dweller and you have a flatmate who loves to cook dinner. Every night he cooks one of three things: sushi, waffles, or pizza. And you would like to be able to predict what you're going to have on a given night, so you can plan the rest of your days eating accordingly. In order to predict what you're going to have for dinner, you set up a neural network. The inputs to this neural network are a bunch of items like the day of the week, the month of the year, whether or not your flatmate was in a late meeting, variables that might reasonably affect what you're going to have for dinner. Now, if you're new to neural networks, I highly recommend you take a minute and stop to watch the How Neural Networks Work tutorial. There's a link down in the comments section. If you'd rather not do that right now, and you're still not familiar with neural networks, you can think of them as a voting process. And so in the neural network that you set up, there's a complicated voting process, and all of the inputs like day of the week and month of the year go into it, and then you train it on your history of what you've had for dinner, and you learn how to predict what's going to be for dinner tonight. The trouble is that your network doesn't work very well. Despite carefully choosing your inputs and training it thoroughly, you still can't get much better than chance predictions on dinner. As is often the case with complicated machine learning problems, it's useful to take a step back and just look at the data. And when you do that, you notice a pattern. Your flatmate makes pizza, then sushi, then waffles, then pizza again in a cycle. It doesn't depend on the day of the week or anything else. It's in a regular cycle. So knowing this, we can make a new neural network. In our new one, the only inputs that matter are what we had for dinner yesterday. So if we know if we had pizza for dinner yesterday, it'll be sushi tonight, sushi yesterday, waffles tonight, and waffles yesterday, pizza tonight. It becomes a very simple voting process, and it's right all the time because your flatmate is incredibly consistent. Now, if you happen to be gone on a given night, let's say yesterday you were out, you don't know what was for dinner yesterday. You can still predict what's going to be for dinner tonight by thinking back 2 days ago. Think, what was for dinner then? So what would be predicted for you last night? And then you can use that prediction in turn to make a prediction for tonight. So we make use of not only our actual information from yesterday, but also what our prediction was yesterday. So at this point, it's helpful to take a little detour and talk about vectors. A vector is just a fancy word for a list of numbers. If I wanted to describe the weather to you for a given day, I could say the high is 76 degrees Fahrenheit, the low is 43, the wind's 13 miles an hour, there's going to be a 1/4 inch of rain, and the relative humidity is 83%. That's all a vector is. The reason that it's useful is vectors, lists of numbers, are computers' native language. If you want to get something into a format that it's natural for a computer to compute, to do operations on, to do statistical machine learning, lists of numbers are the way to go. Everything gets reduced to a list of numbers before it goes through an algorithm. We can also have a vector for statements like, it's Tuesday. In order to encode this kind of information, what we do is we make a list of all the possible values it could have, in this case, all the days of the week, and we assign a number to each. And then we go through and set them all equal to 0, except for the one that is true right now. This format is called one-hot encoding, and it's very common to see a long vector of zeros with just one element being 1. It seems inefficient, but for a computer, this is a lot easier way to ingest that information. So we can make a one-hot vector for our prediction for dinner tonight. We set everything equal to 0 except for the dinner item that we predict. So in this case, we'll be predicting sushi. Now we can group together our inputs and outputs into vectors, separate lists of numbers, and it becomes a useful shorthand for describing this neural network. So we can have our dinner yesterday vector, our predictions for yesterday vector, and our prediction for today vector.
And the neural network is just connections between every element in each of those input vectors to every element in the output vector. And to complete our picture, we can show how the prediction for today will get recycled. The dotted line there means hold on to it for a day and then reuse it tomorrow. And it becomes our yesterday's predictions tomorrow. Now we can see how if we were lacking some information, let's say we were out of town for 2 weeks, we can still make a good guess about what's going to be for dinner tonight. We just ignore the new information part and we can unwrap or unwind this vector in time until we do have some information to base it on, and then just play it forward. And when it's unwrapped, it looks like this. And we can go back as far as we need to and see what was for dinner and then just trace it forward and play out our menu over the last 2 weeks until we find out what's for dinner tonight. So this was a nice simple example that showed recurrent neural networks. Now to show how they don't meet all of our needs, we're going to write a children's book. It'll have sentences of the format, Doug saw Jane, period. Jane saw Spot, period. Spot saw Doug, period. And so on. So our dictionary is small, just the words Doug, Jane, Spot, saw, and a period. And the task of the neural network is to put these together in the right order to make a good children's book. So to do this, we replace our food vectors with our dictionary vectors. Here again, it's just a list of numbers representing each of the words. So for instance, if Doug was the most recent word that I saw, my new information vector would be all zeros except for a 1 in the Doug position. And we similarly can represent our predictions and our predictions from yesterday. Now, after training this neural network and teaching it what to do, we would expect to see certain patterns. For instance, anytime a name comes up, Jane, Doug, or Spot, we would expect that to vote heavily for the word saw or for a period, because those are the 2 words in our dictionary that can follow a name. Similarly, if we had predicted a name on the previous time step, we would expect those to vote also for the word saw or for a period. And then by a similar method, anytime we come across the word saw or a period, we know that a name has to come after that. So it will learn to vote very strongly for a name, Jane, Doug, or Spot. So in this form, in this formulation, we have a recurrent neural network. For simplicity, I'll take the vectors and the weights and collapse them down to that little symbol with the dots and the arrows, the dots and the lines connecting them. And there's one more symbol we haven't talked about yet. This is a squashing function, and it just helps the network to behave. How it works is you take all of your votes coming out and you subject them to this squashing function. For instance, if something received a total vote of 0.5, you draw a vertical line up. Where it crosses the function, you draw a horizontal line over to the y-axis, and there's your squashed version out. For small numbers, the squashed version is pretty close to the original version, but as your number gets larger, the number that comes out is closer and closer to 1. And similarly, if you put in a big negative number, then what you'll get out will be very close to -1. No matter what you put in, what comes out is between -1 and 1. So this is really helpful when you have a loop like this, where the same values get processed again and again, day after day. It is possible, you can imagine if in the course of that processing, say something got voted for twice, it got multiplied by 2, in that case, it would get twice as big every time and very soon blow up to be astronomical. By ensuring that it's always less than 1, but more than -1, you can multiply it as many times as you want. You can go through that loop and it won't explode. In a feedback loop, this is an example of negative feedback or attenuating feedback. So you may have noticed our neural network in its current state is subject to some mistakes. We could get a sentence, for instance, of the form, Doug
saw, Doug, period. Because Doug strongly votes for the word saw, which in turn strongly votes for a name, any name, which could be Doug. Similarly, we could get something like Doug saw Jane, saw Spot, saw Doug. Because each of our predictions only looks back one time step, it has very short-term memory, then it doesn't use the information from further back, and it's subject to these types of mistakes. In order to overcome this, we take our recurrent neural network and we expand it, and we add some more pieces to it. The critical part that we add to the middle here is memory. We want to be able to remember what happened many time steps ago. So in order to explain how this works, I'll have to describe a few new symbols that we've introduced here. One is another squashing function, this one with a flat bottom. One is an X in a circle, and one is a cross in a circle. So the cross in a circle is element by element addition. The way it works is you start with two vectors of equal size, and you go down each one. You add the first element of one vector to the first element of another vector, and then the total goes into the first element of the output vector. So 3 plus 6 equals 9. Then you go to the next element. 4 plus 7 equals 11. And so your output vector is the same size of each of your input vectors. Just a list of numbers, same length, but it's the sum, element by element, of the two. And very closely related to this, you've probably guessed, the X in the circle is element by element multiplication. It's just like addition, except instead of adding, you multiply. For instance, 3 times 6 gives you a first element of 18. 4 times 7 gets you 28. Again, the output vector is the same size of each of the input vectors. Now, element-wise multiplication lets you do something pretty cool. You imagine that you have a signal, and it's like a bunch of pipes, and they have a certain amount of water trying to flow down them. In this case, we'll just assign the number to that of 0.8. It's like a signal. Now, on each of those pipes, we have a faucet, and we can open it all the way, close it all the way, or keep it somewhere in the middle to either let that signal come through or block it. So in this case, an open gate, an open faucet would be a 1, and a closed faucet would be a 0. And the way this works with element-wise multiplication, we get 0.8 times 1 equals 0.8. That signal passed right through into the output vector. But the last element, 0.8 times 0 equals 0. That signal, the original signal, was effectively blocked. And then with the gating value of 0.5, the signal was passed through, but it's smaller. It's attenuated. So gating lets us control what passes through and what gets blocked, which is really useful. Now, in order to do gating, it's nice to have a value that you know is always between 0 and 1. So we introduce another squashing function. This will represent with a circle with a flat bottom, and it's called the logistic function. It's very similar to the other squashing function, the hyperbolic tangent, except that it just goes between 0 and 1 instead of -1 and 1. Now, when we introduce all of these together, what we still have the combination of our previous predictions and our new information. Those vectors get passed, and we make predictions based on them. Those predictions get passed through, but the other thing that happens is a copy of those predictions is held onto for the next time step, the next pass through the network. And some of them, here's a gate right here, some of them are forgotten, some of them are remembered. The ones that are remembered are added back into the prediction. So now we have not just prediction, but predictions plus the memories that we've accumulated and that we haven't chosen to forget yet. Now there's an entirely separate neural network here that learns when to forget what.
Based on what we're seeing right now, what do we want to remember? What do we want to forget? So you can see this is powerful. This will let us hold on to things for as long as we want. Now, you've probably noticed, though, when we are combining our predictions with our memories, we may not necessarily want to release all of those memories out as new predictions each time. So we want a little filter to keep our memories inside and let our predictions get out. And we add another gate for that, to do selection. It has its own neural network, so its own voting process, so that our new information and our previous predictions can be used to vote on what all the gates should be, what should be kept internal, and what should be released as a prediction. We've also introduced another squashing function here. Since we do an addition here, it's possible that things could become greater than 1 or smaller than -1, so we just squash it to be careful, to make sure it never gets out of control. And now, when we bring in new predictions, we make a lot of possibilities, and then we collect those with memory over time, and of all of those possible predictions, at each time step, we select just a few to release as the prediction for that moment. Each of these things, when to forget and when to let things out of our memory, are learned by their own neural networks. And the only other piece we need to add to complete our picture here is yet another set of gates. This lets us actually ignore possible possibilities as they come in. This is an attention mechanism. It lets things that aren't immediately relevant be set aside so they don't cloud the predictions in memory going forward. It has its own neural network and its own logistic squashing function and its own gating activity right here. Now, long short-term memory has a lot of pieces, a lot of bits that work together. And it's a little much to wrap your head around it all at once. So what we'll do is take a very simple example and step through it just to illustrate how a couple of these pieces work. It's admittedly an overly simplistic example, and feel free to poke holes at it later. When you get to that point, then you know you're ready to move on to the next level of material. So we are now in the process of writing our children's book. And for the purposes of demonstration, we'll assume that this LSTM has been trained on our children's books, examples that we want to mimic. And all of the appropriate votes and weights in those neural networks have been learned. Now we'll show it in action. So far, our story so far is Jane saw Spot, period. Doug is the most recent word that's occurred in our story. And also, not surprisingly for this time step, the names Doug, Jane, and Spot were all predicted as viable options. This makes sense. We had just wrapped up a sentence with a period. The new sentence can start with any name, so these are all great predictions. So we have our new information, which is the word Doug. We have our recent prediction, which is Doug, Jane, and Spot. And we pass these two vectors together to all 4 of our neural networks, which are learning to make predictions, to do ignoring, to do forgetting, and to do selection. So the first one of these makes some predictions. Given that the word Doug just occurred, this has learned that the word saw is a great guess to make for a next word. But it's also learned that having seen the word Doug, that it should not see the word Doug again very soon, seeing the word Doug at the beginning of a sentence. So it makes a positive prediction for saw and a negative prediction for Doug. It says, I do not expect to see Doug in the near future. So that's why Doug is in black. So this example is so simple we don't need to focus on attention or ignoring, so we'll skip over it for now. And this prediction of saw, not Doug, is passed forward. And again, for the purposes of simplicity, let's say there's no memory at the moment, so saw and Doug get passed forward, and then the selection mechanism here has learned that when the most recent word was a name, then what comes next is either going to be the word saw or a period. So it blocks any other names from coming out. So the fact that there's a vote for not Doug gets blocked here, and the word saw gets sent out as the prediction for the next time step. So we take a step forward in time now. The word saw is our most recent word and our most recent prediction. They get passed forward to all of these neural networks, and we get a new set of predictions. Because the word saw just occurred, we now predict that the words Doug, Jane, or Spot might come next. We'll pass over ignoring and attention in this example, and we'll take those predictions forward. Now, the other thing that happened is our previous set of possibilities, the word saw and not Doug, that we were maintaining internally, get passed to a forgetting gate. Now, the forgetting gate says, hey, my last word that occurred was the word saw. Based on my past experience, then I can forget about, I know that it occurred. I can forget that it happened, but I want to keep any predictions having to do with names. So it forgets saw, holds on to the vote for not Doug, and now at this element by element addition, we have a positive vote for Doug, a negative vote for Doug, and so they cancel each other out. So now we just have votes for Jane and Spot. Those get passed forward. Our selection gate, it knows that the word saw just occurred, and based on experience, a name will happen next. And so it passes through these predictions for names. And for the next time step then, we get predictions of only Jane and Spot, not Doug. This avoids the Doug saw Doug period type of error and the other errors that we saw. What this shows is that long short-term memory can look back 2, 3, many time steps and use that information to make good predictions about what's going to happen next. Now, to be fair to vanilla recurrent neural networks, they can actually look back several time steps as well, but not very many. LSTM can look back many time steps and has shown that successfully. This is really useful in some surprisingly practical applications. If I have text in one language and I want to translate it to text to another language, LSTMs work very well. Even though translation is not a word-to-word process, it's a phrase-to-phrase, or even in some cases a sentence-to-sentence process, LSTMs are able to represent those grammar structures that are specific to each language. And what it looks like is that they find the higher level idea and translate it from one mode of expression to another, just using the bits and pieces that we just walked through. Another thing that they do well is translating speech to text. Speech is just some signals that vary in time. It takes them and uses that then to predict what text, what word is being spoken, and it can use the history, the recent history of words, to make a better guess for what's going to come next. LSTMs are a great fit for any information that's embedded in time. Audio, video. My favorite application of all, of course, is robotics. Robotics is nothing more than an agent taking in information from a set of sensors, and then based on that information, making a decision and carrying out an action. It's inherently sequential, and actions taken now can influence what is sensed and what should be done many time steps down the line. If you're curious what LSTMs look like in math, this is it. This is lifted straight from the Wikipedia page. I won't step through it, but it's encouraging that something that looks so complex expressed mathematically actually makes a fairly straightforward picture and story. And if you'd like to dig into it more, I encourage you to go to the Wikipedia page Also, there are a collection of really good tutorials and discussions, other ways of explaining LSTMs that you may find helpful as well. I'd also strongly encourage you to visit Andre Karpathy's blog post showing examples of what LSTMs can do in text. And if you haven't seen it yet, take a look at the video on how neural networks work to get some more details on exactly how you go about implementing something like this in code.
Thanks for tuning in. I wish you a lot of luck on your next project, building with recurrent neural networks.